and they vary. But what doesn't tend to happen is for them to just kind of grow away exponentially, like either grow or decay. Well, you have the Maunder minimum where they kind of decay away, but they somehow come out. And so what that kind of tells you is there's some sort of non-linear mechanism that's preventing them from just having exponential growth in amplitude. And that's kind of the thing we're ultimately interested in here. We're working within the framework of the Babcock latent model. So this is the picture where the sun's kind of global magnetic field goes from poloidal at kind of solar minimum through a sort of toroidal phase where it gets wound up by the differential rotation, and then by some mechanism in the Babcock latent kind of picture, it's the emergence of active regions. You get back to being poloidal again at the next solar minimum, but with the opposite polarity. And then you have a cycle and you go back to where you started. Now, the thing with this is that the first phase here, the winding up by differential rotation, is basically a linear process to sort of all intents and purposes. And so is the process by which active regions kind of decay to produce the polar field again. And so that it basically happens because they're somehow twisted north-south. So they have a north-south component, and those north-south components spread out over the solar surface, and they all add up at the end of the cycle to make the polar field. And we actually, you can follow that process quite well with a linear model, essentially, which is what we call surface flux transport. So what this kind of leads you to conclude is that if there's any nonlinearity, or a significant nonlinearity, it probably has to happen in this phase where you go from having a toroidal field inside the sun to having active regions on the surface, so the emergence of the active region. And so this is where, well, firstly, any sort of random variation in the cycle amplitudes has to come from, but also where any nonlinearity that's kind of limiting that variation. So that's the sort of the background. So I want to talk a bit more about surface flux transport. I don't know how familiar people are, but this is the model that's been very successful, and which originally was suggested by Leighton in the 1960s, that you can, or you should treat the radiomagnetic field on the solar surface as kind of a passive scalar. So it just gets transported around both by advection and in this model by diffusion. So this is the sort of equation that BR would satisfy, and you have your advection term on the left here with some surface velocity, and in the traditional model these are large scale velocities. So it's like the differential rotation, perhaps the meridional flow that was added a bit later, and then this red term on the right, that's the diffusion, and the diffusion is basically, in Leighton's model, is modeling the kind of unresolved smaller scale convection, really the supergranular convection. So it's like a mean field model. And this actually reproduces pretty well what happens to the flux on the solar surface. You need this S, which is a source term. So that's the emergence of new active regions, essentially, or new ephemeral region. Okay.
Keep going. Sorry.
Keep going. So let's see if this movie works here. So this is just a movie. Right. This is a movie I made quite a while ago, where the top one is just solving this equation, and the bottom one is synoptic maps of the real sun. It looks like Kitt-Peak magnetograms here. And so you see these new active regions are kind of put in, and then they get sheared by the differential rotation. They spread out because of the diffusion. You have some flux cancellation, but then you eventually end up with a polar field. So at this point in time, where it's sort of cycle maximum, it's got a weak field at higher latitudes, and as it progresses, you end up building a polar field. It's going to be black in the North Pole and white in the South Pole, negative and positive, or whatever it is. And this model actually does pretty well at reproducing the large scale. So you don't reproduce all the small scale. I was going to say noise. I mean, it's not noise. I mean, it's kind of small scale variation, but you don't need that in order to model the large scale field, or at least not to
What do you give the model? You give it the sources, the new activity?
Yeah, so you just give it the new. So in this particular movie, I think I basically looked for each region in the synoptic map and fitted that to a simpler, like a bipolar shape. And you can also just put in more complicated shapes. It doesn't make any.
Yeah.
And so all the rest of the evolution is just coming from the transport equation.
Yeah.
So it's a purely. Yeah.
Do you give it the measured velocities too?
Yes. So
okay.
Measured is in this model. I think I just kept the velocity constant at a simple function.
Okay.
You'll see later on that I sort of fit it to the data. Because of course it's not like there's no physical law telling us what this velocity is. We have to put that in as a.
Yeah.
So the differential rotation is fine. We know what that should be, but the meridional circulation is less certain, basically.
H0 is supergranular.
It's a supergranular diffusion. Yes. So, yeah. Okay. Right. So what we need to look at is what happens with individual. So the equation was linear in BR. No, I just moved it. But so that means that the solution is basically the solution for each individual active region all added together, just mathematically. So it's useful to look at individual active regions. So this is a simple active region here that I put on the equator. It has a tilt angle, so you're never going to build up a net polar field from that region if it's not tilted, because you'll just cancel out the positive and negative. And you see what happens. This second one is like a latitude. So the y-axis is sine latitude, and the x-axis is time, and it's the longitude average. So like the integral of BR in longitude. And so you see what happens is that because of the meridional flow, it's the flux in the northern hemisphere is pushed to the North Pole, and the southern hemisphere is pushed to the South Pole over about 2 years or something like that. And you end up with because of this, you end up with a kind of asymptotic state where you've got a polar crown in each hemisphere, essentially. And this right-hand plot is showing you it's the axial dipole moment, so the north-south dipole moment, which is just a convenient measure of the polar field, essentially, the poloidal field, I should say. So it's just the integral of BR times sine latitude. And you see, of course, it starts with some value, but it gets amplified, and then as you reach this kind of steady state, it flattens off. So the thing that makes a difference to this is what latitude you put the region at. So if I put the region, so this is showing you it's getting higher in latitude, so starting at 12 degrees and then 24 degrees. And you see, as you move higher in latitude, less of the blue flux gets transported into the opposite hemisphere. And if you put it high enough, then basically none of it does, to all intents and purposes. And when none of it gets transported into the other hemisphere, you don't build up any polar field in sort of asymptotically. So it just decays away. And at the end of the solar cycle, let's say you basically have no polar field, or your dipole here goes to zero. And so there is some critical latitude where below that, the polar field contribution goes to zero, and above that, the polar field contribution goes to zero, and below it, you get a non-zero contribution. And the closer you are to the equator, the more it's going to get amplified from whatever it was initially. So that's the kind of key thing, really, that controls everything else, is what happens to an active region. And the whole thing is just the sum of loads of these active regions. What's this? So this is the same plot again.
There's a question from Phil.
Yes.
Phil, go ahead.
Yeah. Hi, Anthony. My question is simply this: you're solving a deterministic equation in terms of a diffusion coefficient, but of course that's a representation of a random walk.
Yes.
So I was just wondering what the fluctuations would contribute to this, the fluctuations in that random walk. What are the amplitudes?
So that's a good question. I don't really know the answer of what are the amplitudes. I'll show you later on what the effect of varying the diffusion coefficient is, and that will give us some idea. I think it's one of these things where people try and fit it from observations, and it's just really difficult to do.
Yes.
Because it's not perfectly a random walk. So it's sort of unclear what you should do.
But if those fluctuations were of order, say, a half of the mean or something, then it would qualitatively change this picture a bit. So I suspect they're not
I think so.
I suspect they're not that big, right?
I think so. I mean, it's hard to, because it matches the real thing quite well.
Okay.
You sort of hope that it's a reasonable approximation.
No, and I think that if you consider the supergranular size compared to the surface, to the whole surface, then the diffusion approximation is not so bad.
I think, yeah, I mean, of course, it's not independent of the magnetic field. Like the active regions probably slow down the diffusion to some degree, but it doesn't actually make that much difference. You can put that effect in a kind of parameterized way.
Yeah.
And it's not
Okay.
sort of critical, I don't think. Although I haven't shown that here. Thank you.
Thank you.
Yeah, so what I was going to say here is that what you can do that we didn't realize until sort of not that long ago was you can just predict this final contribution of an active region with a simple formula. And I'm not going to, I don't want to talk about the maths of this, but it basically, if you take the sort of limiting dipole moment divided by the initial one, so how much it gets amplified by, essentially, it is actually a Gaussian function of latitude. It turns out, so you can show this analytically from the equation, or it was actually first of all shown sort of empirically, and the width of this Gaussian, essentially this lambda r, as we called it, it's kind of a dimensionless parameter. So it's the ratio of the diffusion to the, so delta U, I'll probably show you later on, is a parameter that comes in the meridional flow, basically. It's like the gradient of the meridional flow at the equator, something like that. And the, yes.
Sorry, is B1 0?
This is the axial dipole moment, so
Is
the
it
north-south
actually
dipole.
unsigned flux or?
No, it's the north-south dipole moment.
Oh, no, okay.
So the integral of BR times, let me get this right, BR times sine latitude.
Okay, all right.
Times some normalization. So yeah, so it's really just the sort of north-south component. So the width of this Gaussian has a form that we know, and so what you can say from this is that if a region is nearer the equator than this lambda r in radians, if you like, then it's going to be its dipole moment is going to be amplified, so it's going to contribute to the dynamo. If it's further from the equator, then the dipole moment is going to basically go to zero and not contribute anything. So it's kind of a parameter, and it's sort of you could think of it as a balance between poleward transport by meridional flow and equatorward transport by diffusion, something like that. You need something to diffuse across the equator in order to make a polar field, because you've got to have flux left in both hemispheres. So this was all described in a sort of series of papers. Ji Zhang's original paper, they sort of empirically found this Gaussian, and then subsequently we sort of managed to show this from the equations that this is what you should get. But the key thing here really is just that you have this lambda r that measures whether a region is going to contribute or not, and this lambda r is only a function of the parameters in that transport equation. So if we can somehow observe or fit the parameters in that transport equation, we can work out which active regions are important and not, or not. Kind of the logic. So let's go back to the question: what about nonlinearity in the solar cycle? And so there's sort of two possible nonlinearities that you can see at the surface. There could be other nonlinear things going on beneath the surface that we can't address with them. The first is what's called tilt quenching, and this is just the fact that, or the idea that stronger active regions, bigger active regions are less tilted. And so the idea would be if you have a solar cycle which is stronger, you probably have more stronger regions, and those regions are probably less tilted, and that will therefore produce less polar field than you would otherwise expect. So it's like a limiting mechanism. And this paper by HAO and Zhang and collaborators is basically the most up-to-date analysis of whether tilt angles really are different in stronger cycles. And I think they basically conclude that yes, but it's quite a weak effect. Like it depends how you measure it to a reasonable degree. You've got to bring a lot together to see the effect. But it does seem to be a real thing. But in the literature, there's a lot of controversy over whether it's real or not, because it depends how you look at it. But so theoretically, one possible explanation, you can somehow show this from the thin flux tube model. I don't remember the details, but basically somehow it weakens the Coriolis force as the flux tube is rising if the tube is stronger. You can actually also get this just from looking at the surface. So you sort of one of the people who likes to think the dynamo is right at the surface. The fact that you have inflows towards active regions, and if those inflows are stronger for a stronger region, then that will naturally limit the tilt. And so there's different ways it could arise even. But the other possibility is latitude quenching. So this was what I had in the title. And this is the idea that active regions emerge at higher latitudes in stronger cycles. And I cited Ji Zhang again here because this was really the first paper that sort of, as far as we can tell, that linked this idea to the nonlinearity of the dynamo. So we'd known for a long time that active regions emerge at higher latitudes in stronger cycles. This was in Waldmeyer, I think, originally found it. And as far as I can make out, this is one of his plots. And it's basically showing you that, well, you can't read these numbers, but the top curve is like a strong solar cycle. And then as you reduce the sunspot number, the latitudes of the sunspot bands go down. This was in a paper in the 1930s. But he wasn't thinking in terms of the kind of nonlinear effect on the solar cycle. So that's a definite possibility as well. So of course, if they emerge at higher latitudes, it means you're more likely to be above lambda r. So your dipole contribution is going to get killed off rather than amplified on average. Okay, so what I want to give you the sort of results first, and then I don't know how far we'll get through the methods. It's kind of the logic. I don't, because I haven't given this talk before exactly, so in this format. So here are the results. So what did we do? So we basically reconstructed 6 solar cycles worth of active regions, essentially. And it goes, I didn't put the cycle numbers here. I think it goes from cycle 16, so about 1923 or something, up until cycle 21. Yes, so up until 1985. And that's because we did all this from Mount Wilson data, as I'll show. So, and that was the kind of period we have. And this particular plot is every dot is an active region. They, of course, all overlap a lot, but the color is the contribution to the axial dipole from that region. So like the asymptotic value of the B10 for that particular region. And so you can see really clearly that the cutoff, like everything above a certain latitude contributes nothing, or not very much. These lines are just a plus and minus 20. It's not exactly the value of lambda r. That's somewhere lower.
Was it determined? Because you didn't set a latitude threshold. You determined it at some.
Yes, I'll have to explain that.
Okay.
It's an optimization essentially. Okay. I mean, it's always going to be true that things nearer the equator contribute more. It's just a case of where the cutoff is.
Yeah.
Longitudinal average. How can you pick one active region?
Oh, they're not long. So these are just all the active regions in time and latitude. I haven't longitude.
So this one dot is how many?
Each dot is an active region.
One active.
But there's so many of them that you can't see all the dots. So
you just highlight some dots.
So no, they're all the dots are colored, but I put the darkest ones on top, I think, or something. And so you could sort of see the strongest ones on top of the others. But so the color means the sign, right? So it should be that it alternates in sign from one cycle to the next because the polar field flips. And you can, I think if you squint, you can sort of see that it goes red, blue.
Yeah.
Yeah, this is really slow here. Red, blue, red, blue. But of course, you have a lot of scatter, and this scatter is real. So this from looking at magnetograms, right?
So
Always noise.
no Mount Wilson equivalent data after 86.
There is so after that we have magnetograms, so it can be extended. But so far we've just stuck to one data set, and this was the time for. I think after that there's problems with the coverage of and the quality of the Mount Wilson data that we're using. I understand. There are some after that, I think, but yeah, this was the sort of set where we had good data essentially. It actually also goes back earlier, but we have some issues earlier with some of the measurements. I have in fact extended it earlier, but I'm not going to show that here because I haven't made all the plots. But that's a sort of summary. So I'll tell you how in a bit how we actually reconstructed this. But to sort of answer the question of the title, there's two ways we can look at it. So the first thing we did is just sort of look directly at the active region. So firstly we have the latitude quenching, if you like. So this is a plot of the latitude, the average latitude over all the regions is on the y-axis. In fact, it's the sine latitude, and then the x-axis is the strength of the cycle, measured in a sort of relative way. So, relative to the mean strength over all the cycles. And I've actually separated the hemispheres here, I think, to give us more points on the plot. And you see there's quite a good correlation between the strength of the cycle and the latitude, which we sort of expected, essentially. But it's good that we did actually recover it. The tilt is less clear. So the tilt here I'm defining, you don't need to worry too much about it, but it's basically the angle that the two centroids make with respect to the equator. But we measure it in a kind of polarity agnostic way, if you like, because we were trying to compare to something else that was already done. So it's really just the angle, and we don't care whether it's which one is positive or which one's negative. And so then what we do is do a fit for all the regions in a given cycle, or a linear fit with latitude, essentially. And the coefficient of this linear fit is what I'm going to plot in the picture. And this is what other people have done, essentially. This is what they did in the cases where they managed to find a relation. So this is kind of the logic. And so this is the plot. So this best fit coefficient T lin is on the y-axis, and x-axis is the same thing. It's the cycle strength. And you can see that there's, of course, a lot more scatter within each cycle. You could see that from the red and blue dots before. But there is a trend. There is a significant kind of negative correlation. It's just weaker than the one for latitude. It's also not clear that it's linear, but obviously we don't have enough data to say much about it. So the conclusion is sort of that you can sort of make a relation, but it's certainly not as strong as latitude.
And it could be driven by latitude, right?
Yeah, so this
relationship between the tilt and the latitude.
Yeah, and I'm thinking
is this correlated with latitude?
But we've kind of got that because we're fitting the correlation with latitude. We're fitting the linear fit with latitude. So I think we've taken that into account.
Yes.
Unless it's non-linear. But they tried the Zhao paper that I mentioned before, tried different functions here, I think. They tried some non-linear functions and found that it was basically no better. Or at least they couldn't tell. So the linear functions seem to be. Yes.
But left claw, I would expect an anti-relation because you said at high latitude, this is the mean latitude of the active region. Mean latitude of the active region higher the ones that create lower dipoles.
No, yeah. So when you have a strong cycle, you have a high latitude, so it creates a lower dipole, and then that limits the next cycle to be weak again or weaker. because we're trying to avoid having a nonlinear thing where a strong cycle makes a high polar field and then it just increases exponentially. So this is the right way around. So if you have a strong cycle, it makes less polar field, and that limits the thing. That's the nonlinear effect.
Okay.
And the tilt is kind of the other way around. When you have a strong cycle, they're less tilted, so they make less polar field. So that's one way of looking at it. There's also a more sophisticated way of looking at it, which came from a paper that Talafa. We have some feedback on that? Sure.
Maybe you can mute those people.
And maybe somebody unmuted.
It must be just someone else that we're hearing.
Yeah.
So the Talafa, who was working with Christoph Petrové, made a nice paper where they sort of did like toy models, if you like, just with very simple active source term in the flux transport equation. But they looked at the relative importance of latitude and tilt quenching, just kind of theoretically, if you like, and they found that the relative importance actually depends on this lambda r parameter. So this is their plot. So now the x-axis is this lambda r parameter, so this critical latitude, if you like, and the y-axis, I have to get right here. This is the how much it affects, how much latitude quenching affects the polar field relative to how much tilt quenching. We don't really need to worry about the precise details. And basically, and there's two different curves. The orange one is the one that corresponds with what we're talking about here. The dots are all the lambda values from different people's published simulations, I think. And so they basically fall on these curves. And then, but the key thing is the one here is the sort of point where you go from latitude quenching having more effect to tilt quenching having more effect. And this happens at a lambda value of about 10 or something like that, 10 or 11 degrees. I think it's measured here in degrees. So it's a degrees latitude. So, okay, I put a line there. So what we did in our work paper is now on the right. We basically tried to fit this lambda value to the observations, which is a somewhat long drawn out process that I'll talk about if we have time. So, and we find the lambda value. So this is the y-axis here is some kind of measure of the goodness of fit, essentially, or the inverse of that. And we want to minimize that. It's like the error in the in some objective function, and you can see it's quite nicely minimized at a value of about 6 degrees. But this is nice because it's well to the left in this plot, the left of the dashed line. So according to their analysis, latitude quenching should be the dominant thing. And that seems to be consistent with what you see in the previous slide, where with the much better correlation for latitude quenching. It wasn't at all obvious that this was going to be the value of lambda, because the previously published models have values all over the place, basically. Now, it doesn't say on here whose model is what, so I can't name any names. Probably this black dot is one of mine, I imagine, but who knows? So this was kind of interesting, but it really does seem to show that the latitude quenching is having much more of an effect. It's not to say that tilt quenching doesn't do anything, but it doesn't seem to be the dominant thing. Okay, so the rest of the talk, I think, is basically going to be trying to explain how we actually arrived at this conclusion. And I think the actual data that we have is going to be useful for other things as well. It's not only to answer this question, because we basically have a model for all the active regions in that sort of 6 cycles period, most of which we don't have magnetograms, right? That's the key thing. So now, this is the where it all started. So I saw that Kalevi was on the Zoom. He's in this picture here. This was an EC team that was led by Alexei, and the idea was to try and reconstruct basically magnetograms over the 20th century. And a series of papers was written by members of the team about doing this. And in fact, also a PhD thesis. So standing at the back here is Eero Virtanen, who was doing his PhD in Oulu, and his thesis was basically on this work. I haven't probably got time to show you all his results, but basically what I've done is to sort of take his basic method that they mapped out and go back through it and try and tighten up all the uncertainties and make sure that everything is working as nicely as we can. But Eero basically showed that the thing will work, and that gave me the confidence to spend time trying to do it myself. So what do? We start out from, the whole thing is really based on calcium K observations, and what had been done before the start of this by Luca and Alexei was to create synoptic maps of calcium K from Mount Wilson. And so basically you have all these, I think they call them spectroheliograms, that sort of full disk images of calcium K, and over kind of most of the 20th century. And they did a lot of work trying to sort of calibrate them and normalize them so that you can combine them into synoptic maps. And you get this is I guess a super synoptic map where they all stack together, and it gives quite a nice data set. So I'm working from the synoptic maps in this project, where they've been kind of calibrated to a sort of normalized intensity. Now, the reason that this is good is because we know that calcium K is quite a good marker of magnetic flux on the sun. Probably seen this before. What do I have here? So this is a plot from one of Alexei's papers showing this top picture here is a calcium K image with the sort of concentrations of higher intensity outlined, I guess. And the bottom one is a magnetogram. And basically the two things match together pretty well. So it's not that you can say that an intensity of 3 is a bit high. An intensity of 1.3 in calcium K is 75 Gauss or something like that. It's more like, you know, that where you have an area of high emission in calcium K, it's going to be a region of strong flux in the magnetogram. And so what we do is, so if you just did a sort of point-to-point correlation, you'd get a wide scatter. But what they did here is integrate over the entire region, essentially, the magnetic flux. This is for a time where they had magnetograms. And then integrate the intensity of calcium K, and you do actually then get a good correlation. You can, in fact, just count the pixels above a certain level or something like that. So that's the level that we're sort of matching at. So for these global scale things, I think it works quite well. So this is a picture from our paper showing the sort of process of putting magnetic flux or matching with magnetic flux. So I have to.
But when we have sunspots, that turns around, right? So this seems to work for the whole region, perhaps, when you have like all the extended network. But if you compare, because calcium does show sunspots, no?
Yeah, I don't think it affects this.
So your intensity goes down where the magnetic field.
Yeah, well, I don't have the plot, but it kind of goes like this. But the turnover is not very much. I think it's sort of a little bit at the top. So we sort of feel like it's the best we can do in some sense anyway. But
yeah, okay.
I think the correlation is including those in that plot. It's including the sunspot, I think. So this is what's this? So the top left-hand one. This is one of the synoptic maps, just chosen for some arbitrary Carrington rotation. And this, we put a threshold to get rid of the kind of weaker regions, and you get this top right picture of these kind of individual plages, I'd like to call them. So this is during a time where we have magnetograms. So obviously we validate it so that we have a whole cycle where we overlap with good magnetogram coverage from Kitt Peak. So this is a magnetogram for that rotation, and then this is just if you take the magnetogram and you take the regions above a certain threshold in fields, so 50 Gauss or something. It's 50 Gauss. And you get these regions, and you can see just by eye that they correlate quite well with the top one. The bottom one here is just actually an overlap of the two to see where they correspond. But this bottom one here is the most useful, I think, because it's showing you the so it's coloring in all the plages based on size. So we put a size cutoff. We found that below a certain size, they don't correspond very well with the flux. So we cut those off and leave basically only the active regions. And occasionally you get one like this white color. This top right thing is it's unipolar in the magnetogram, right? Its other polarity is actually sort of a distance away. It's not managed to join up, and we have to throw away the unipolar patches. But there's basically few of them, and so we found that just filtering the plages by size gets rid of these kind of problem cases. So then we have to. The problem is that that only gives us the flux. It doesn't tell us the polarity. So what we're doing for the polarity is sort of two things. The most exciting one is that Mount Wilson actually has measurements of the polarity, because although we don't have magnetograms for the whole 20th century, we do have individual measurements in sunspots where you have a strong field. And these are just some random images from the archives. So of course they're hand drawn and they've been digitized, and someone has had to type in all the numbers for the polarities. But well, it's actually they give you the strength. I think we can't even read this, so I won't bother trying to explain. But they basically have all these individual point measurements, and if you ever got a strong region, there's quite a lot of these measurements. And it's something like the flux in Gauss with the zero missing, or I don't remember. It tells you whether it's positive or negative, which is called something like N and V, just to confuse the issue. But it's confusing because the coordinates are written in almost the same way with an E and an N. But that's basically how so you can see this guy here has, yes, I think this, maybe R is positive and V is negative. I forget. They've actually gone through and digitized all of these drawings, and there's a lot of them. So we have this database that's now there. So it's best to illustrate with this same example again. So the top left-hand one is purely showing the sunspot polarity measurements. And you see there's loads of them, basically. They cover pretty much every region, at least in this rotation. And you can see quite clearly that you get opposite polarities within each. So here's the real magnetogram is on the middle right here. And you can see it actually does pretty well at getting the real polarities right. So what's this? So this middle one is where I take the plages and I fill in the polarity information we have. And of course, there's some that don't have any measurements. Can be like an actual gap in the data, typically. And there's some that do. So the ones that don't have any measurements, I don't know if you can see this, but they're kind of outlined in magenta, I guess. And the ones that have measurements are outlined in green, cyan blue. And then we have to fill all those other pixels as well. So you can fill them with nearest neighbor if we've got some polarity information. The ones where we don't have any information, or where we have a problem like it's all one polarity or something like that, then we don't use the observed polarities. We just fill them in according to Hale's law, essentially. So you make the rightmost pixel the leading polarity for that cycle, and the leftmost pixel the opposite, and then you do a sort of nearest neighbor. And then you get this final map. But you see the coverage is actually quite good. And this is not like a cherry-picked example. At least over this cycle 21, where we have the magnetograms to compare with, you always get basically a similar percentage of pixels with measured polarity information. It's something like 76 or something. So what is this? Okay, I've forgotten what. I think it's the percentage of pixels with correct polarity according to the magnetogram for this period.
But also if you assume it's all hidden.
Yeah, so the blue one, if you throw away all the measurements and you only fill everything by Hale's law, you already get 68% of pixels with the correct polarity. So that's actually that's good because it means in principle you can do something for periods even where we don't have the sunspot measurement. So we might be able to push back further in the past with only with calcium K. I haven't tried to do that for properly, but and you'll still get some signal essentially. But it certainly improves it to have the sunspot measurement. I thought it would improve it more, to be honest, until I tried repeating the exercise, but it's there's still uncertainty around the measurements. There are some uncertainties in the timing, and there are of course gaps in the data where there's no observations from that day and so on. So okay, so this is a minor thing, but you find that about 6% of the regions are anti-HAO in the magnetograms with this method of selecting them. And so what I do when we have no observations and we're filling it by Hale's law, we sort of arbitrarily flip 6% of them, and then have to run an ensemble of different realizations of this. So that's one uncertainty. I don't think that's a crucial thing for the results, but it's something we should be aware of. Then we have to set the flux. So that gave us the polarity, and now the flux I said it's basically proportional. You have this correlation, but there is some scatter. So this is showing you actually measured from my data the size of the plage region essentially on the x-axis and the flux from the magnetogram on the y-axis. And you can see that there's a correlation, but there is a scatter, and the scatter is the larger the size. So we also choose the amount of flux at random from a kind of normal distribution whose width depends on the size, because we felt that this level of scatter was too much to ignore, and so we have more randomization needed. We've got to do an ensemble for this as well, essentially. So the thing gets complicated. That's the but there is a correlation. So we have some hope that it's reasonably accurate. So one way so this is a kind of validation for this cycle 21 where we have the magnetograms. It's just the cumulative flux over all the regions. The black dashed line is the magnetogram, and the red one is the case with the sunspot data, and the blue is the case where we don't use the sunspot data. And it basically has approximately the round amount of flux. The sort of fact that it's too low here is because there are some rotations that are missing in the calcium K, but not in the magnetograms and so on, because they were not both from that. So we sort of underestimated it. But you see a little bit here the effect of the sort of randomization that I talked about. There's a bit of spread, but it's not very much. It doesn't affect the flux very much. This is now a more important thing for the point of view of the dynamo question, which is the dipole moment. So it's the same thing as the cumulative axial dipole. This is now at the time of observation, not the asymptotic one. And you see that the red, this is kind of interesting because the red case, when we have the spot measurements, we do quite well at matching the dipole. But when we always use Hale's law, we overestimate, this is negative here, so we overestimate the dipole by about 30% or something like that. And I spent a long time trying to work out exactly why that is and whether we can correct for it in a clever way. And I came to the conclusion we just have to multiply by or divide by 1.3 because it's to do with the if you always assume everything is perfectly bipolar in shape, you overestimate things because the multipolar regions tend to have a lower dipole moment, but there's no way you can know which ones they are without having the polarity measurements. So although it doesn't, it sort of tells you the polarity measurements really are adding information about the kind of structure of each region, I think. So for the whole earlier period where we don't know the correct answer, whenever I have to fill a region with no sunspot measurements, I just divide it by 1.3. Okay, it says that here. And this was something I think that Eero didn't do in his original work. So I think he basically compensates for it by changing the parameters of the flux transport model. So this is now just a summary of all the regions. In the top panel, they're colored by the leading polarity flux. So you can see Hale's law, and you have this sort of 5 or 6% of exceptions with the wrong polarity. In the you can of course see cycle 19 is really strong here, and that you can also even see the fact that it's higher latitude, as we were talking about. The second one is the dipole strength at the time of emergence now. So you haven't evolved them, so you don't get this latitude cutoff effect. And you can see the fact that they alternate in sign quite clearly from this. And you can also see the scatter. Okay, and the last one is just showing that the total amount of flux in the plages is basically reasonably correlated with the sunspot number, which is sort of reassuring. So it's giving us the cycle variation. There's a bit of a gap here in the 1938-9-ish, where we have a lack of observations. And I don't like filling in unobserved things, so I didn't fill in any unobserved. I didn't invent active regions to fill those periods. And yeah, the referee seemed happy with that, so it's okay. Yeah, but you could, of course, invent active regions to fill this period. What we want to do is use Kodai-Canal data to fill that period. And I think we're going to be able to do that, because most of the rotations you have an observation from Kodai. So that's quite promising. So the last phase of the sort of method here is fitting the flux transport model to calculate the lambda R, or fit the lambda R. And the way we did this was thanks to Andres here. We used the polar flux kind of proxy coming from faculae count. So counting white light faculae in white light images, and then going back and reconstructing how strong the polar field was as a function of time. So this data set has been around for a little bit, and we use that as our ground truth. So in the top plot, I don't know if you can see it, it's like the shaded region in the background. So there's an uncertainty on the ground truth. That's the shading in the background. The solid lines here are the north and south polar fields in our fitted flux transport models, and we have the ensemble is coming because of these random things that I talked about in filling the fluxes and the polarities. But you can see it's not that much of a problem. And this is what the dipole looks like. I'm not sure what we do with that information, but you can see it varies from cycle to cycle. The bottom one now is a butterfly diagram of the optimum run. So I basically optimize set of parameters in the flux transport model. That's listed here. So there's our equation. So my meridional flow, I have a functional form that lets me choose the shape. So it's always got one peak in or one hump in each hemisphere, but you can move how close to the equator is the P parameter, P0. And then this delta U that we had in earlier, that comes at the front end. That's the slope of U theta at the equator. In this next plot, I'm actually not plotting delta U, I'm plotting the maximum amplitude flow. This was for comparison with something else, but it's basically just the maximum amplitude of the flow. So it's just directly depends on delta U. So what I'm showing here are so I did a whole load of runs of the flux transport. So my optimization method was not at all sophisticated. It's just brute force, run the thing loads of times, like 1,000 times or whatever, 10,000 times, and explore the entire parameter space. I wanted to make sure that we really did explore the full parameter space. And we have this eta naught, we have P naught, we have V naught, and we also have the initial condition, so another parameter in the model. And what this is showing you here is actually, it's selecting, so the y-axis here is the error in the polar flux against those observations in the faculae. I think it's the mean squared error or something. And then each dot is a different simulation with different parameters. And you see that it selects the shape of the meridional flow quite well, to 1.8 or something. But it doesn't select the eta naught and V naught particularly well. But that's actually sort of an illusion, because if you non-dimensionalize this equation, you'll find that the solution only depends on the ratio of E to naught of it. So if I instead I plotted lambda r here, which was basically the ratio of those things, then you see it does select it. So from this kind of work, we can't independently select the optimum E to naught and the optimum V naught. You just select the ratio, and then somehow you would need additional information if you wanted to try and select them individually. So I don't know how historically whether we have any hope of doing that. With modern observations, we can try and measure the meridional flow in other ways, right? So we could try and do that. So, and this is what we had.
One, you can pick one.
Yes.
The other follows.
Yeah, you can. Okay. So it's not
Fusion, maybe.
you can't just pick anything. There's a range where it works, and then it's sort of. I haven't got a plot of that, but but it's quite. You have some freedom still, essentially. Isn't
Yeah.
it? So the initial condition is also not very strongly selected, and the reason for that is because it doesn't. As long as you pick something sensible, it basically doesn't influence things for the whole time. It sort of. So this bottom plot is. Oh, this is the case where all the regions are filled with Hale's law. There's no sunspot measurements used. And you can see it still manages to select a lambda r, but it's not as strongly selected. And if you actually look carefully, it's not as good a fit to the polar field. It's not terrible, which we kind of expect because we saw that it still gets the polarities right 68% of the time or something, but it's not as good. And it selects a slightly different value, but the bottom of this thing is fairly flat, so I don't think that tells us anything significant. It's basically consistent, and the same for P.
But there is a possibility that you could make your in-painting algorithm a little bit more sophisticated
Yes.
to optimize
Exactly.
not just the match between the specific pixel polarity, like specific pixel polarity, but something like a macro quantity on the region. And so your strategy for in-painting will change slightly depending on the region and
Yeah.
may help.
So if we have a way of saying purely from calcium K that there's like 3 sunspots in this region or something, then I can see that you could somehow say, oh, it should be multipolar, or it should have different peaks. But I don't know whether that's possible or not. I'm not convinced of this, but in principle, it's something that we can try. Because I think, and of course, we don't only have calcium K.
I mean,
in
for
principle,
example,
we have some.
your trailing polarity will be more spread out.
Yeah,
And so you could have a simple in-painting rate. So how many pixels do you advance as you grow? Could be slightly different from the leading polarity,
Right, yeah.
and slightly different for the trailing polarity, and as a single parameter that you can feed to your validation.
yeah, that's an interesting. I think that would have an effect because there's a paper by someone, I think in the Japanese group, where they basically make the active regions asymmetric and show that it does change the dipole of the whole cycle by 20%.
I mean, this is pretty good. I'm
Yeah.
just thinking that that it may be something like if you imagine this as something you're filling with paint, the rate at which you drop the will make it so that the whole area gets more of one polarity and then the other, or something like that.
Yeah, I think that is a systematic thing, right? So it would make sense to incorporate it.
I don't think it changes your results in any way, but to produce a higher quality estimate.
I think it won't change these results, but if we're trying to do other things with it, the better the model is.
Yes.
I mean, I think the last slide here is just a plot of the data gaps, which probably it's hard to interpret. But what's this? This top plot is the percentage of pixel coverage. What on earth that? Okay, I've forgotten exactly, but it's basically how much of the time do we have calcium K, I think. It's not how much of the time do we have sunspot measurements, it's how much of the time do we have calcium K from Mount Wilson. And it actually would get worse if we carried on the plot, it gets worse as in recent times. But there are some gaps at so these are the gaps that really where we're missing whole synoptic maps in the late 1930s, and that is definitely something to try and fix. And similarly, these earlier periods where we're missing quite a lot. Bad part. This is a measure of the. So sometimes you have a synoptic map, but you've not quite got enough observations to fill it, and so some of the plage you can kind of see there's something there, but it's really distorted, and I couldn't use those. And they're what I call bad plages here. So I think this, in a way, the next step would be to try and fill in these gaps. And with the Kodai Canal data, we can also, in principle, go earlier. It goes back to like 1905 or something like that with continuous calcium.
And it goes also very close to the present.
Yes. There's of course
have more cycles to validate.
There's no point. But closer to the present, but I can just extend with magnetogram. But for validation. Yeah.
For validation,
Exactly.
Yeah, not for trading but not as a substitute to the actual magnetogram when we have it.
Yeah.
That's actually another 40 years.
Yeah.
Yes, I've not in the paper. We decided that we just stick to one data set, and we don't have to have the additional complication of merging the two together. But of course, we should be able to quite easily do that because we have this whole cycle of overlap. It should be quite straightforward to extend to the present. So that's something I'm going to try and do. And I would quite like to simulate the corona over this whole time as well. Once we've got the surface complete. But there's lots of things we can do with this. But I think it's just quite amazing to me that you can actually reconstruct the polar field that well just without having any magnetic data. Okay, thank you.
Right,
that's basically
you.
it.
So, we've had quite a bit of discussion, and we can have any questions in the room and also online.
I have a kind of maybe a dumb question coming from a place that's not really familiar with this stuff. So, in your flux transport, when you look at an active region, and you had the measuring how much flux goes to the poles, active regions obviously emerges and then decays again. So, what fluxes are you using to determine how much goes to the poles? The maximum of any active region?
So we don't know that. Especially for the historical data, basically only have. So I'm only using observations at central meridian. So it's basically whatever it happens to be when it crosses central. So this is it's a problem. So we're probably, in some sense, we're then going to underestimate the flux, but
Because you're just
because the flux is an arbitrary parameter anyway, it's sort of relative more than absolute.
But decay is a very slow process.
Yeah.
So for the majority of your regions, you're not going to underestimate significantly. It's only if the thing was emerging when it was crossing central meridian that you're going to have like some more. But if it is fully formed and slowly decaying, then it's maybe not that bad. There is always underestimation, but
you can of course measure that. I haven't got a plot of it, but you can measure how much you're underestimating, but it's then resolution dependent as well. So it's hard you've just got to pick what resolution you're interested in, and then that's going to determine how much you're underestimating. So it's hard to disentangle the two things. But people have tried to, I think Lisa Upton has tried to measure this, and you're underestimating by some 20% or whatever the total flux, but it's not massive. In principle, we have the daily calcium K images, so you could try and say when is the maximum flux region by when is the maximum size of the plage. I'm not sure anyone's tried to do that, but you've got the problem that you've got to make sure they're very well calibrated with each other, the intensity. So I don't know, but it has some effect, but only on the.
You can also, when you're fitting the simulation, have a fitting parameter that is global to all regions. I don't know if you did that already. So when you're fitting the polar field, do you have like a calibration factor in your fit? No,
we don't need one. That's the interesting. But I
think that's really interesting. Of course, some of that will be absorbed by the other parameters, less diffusion and maybe a little less, or a little bit more flow and less diffusion that will account for something like that. But if you want to, this could be another way of quantifying that. Like if you have a calibration factor, how different from one it is, and if it is less than one, maybe that's what's in it.
Yeah, I mean, it's sort of, yeah, that could well be the case. The trouble is, you can't, it's difficult to disentangle that from the other parameters in order, because we're only looking at the active, so to get the polar field, we have to specify the other parameters, and then, I don't know, it would be, you could look for it in the recent period where you have the negative.
So Phil has a question. Phil, go ahead.
Yeah, thanks very much. And thanks for visiting. I'm sorry I didn't know you were here and I would have come in. Anyway, I have a sort of, as usual, a philosophical kind of question. And so I'm just wondering about the context of your work. I think I understood what you did very well. I think you explained it very well indeed. But I have a question, which is, we have a whole lot of dynamo models, all based upon sort of the ideas in MHD. We have tachoclines, we have a distributed kind of dynamo, we have these wreaths inside rapidly rotating stars, we have interface dynamo, we have dynamo waves, we have, so I'm just wondering, and feel free to respond, but I'm going to throw down a challenge and say, what makes people think that what we see at the surface has anything to do with generating or modulating the magnetic field that we see varying on the sun? It's a slice through a three-dimensional volume in which energy is coming out from the interior over a very narrow surface. And it seems to me a little bit guilty of assuming the anthropic principle, which is that what we see at the surface actually is relevant to determining what's going on in the interior. So as I said, it's a philosophical question, but it's one I'd like to hear your opinion on.
Yeah, I mean, I'm sort of, although we've made this assumption, I would say I'm kind of the same opinion. That I feel like it's consistent, at least, but we're sort of testing whether that picture is consistent with itself, and I think it kind of is, but I don't think we can make any claim that it's causal. If that, it can still be that we're just seeing the sort of signature at the surface of something that's really going on underneath. But there's quite a lot of aspects that at the surface that you've still got to explain. So it's kind of interesting. I don't think it seems to me that you can't claim that it must be a kind of a causal thing, the Babcock-Layton dynamo, because we see it. I think it's still possible that we're just seeing a sort of side effect of the real.
But there is the work of Robert Cameron where they are using, that one is pretty strong.
Yeah.
That is a very strong,
Yeah.
So
where
there is
you integrate the toroidal
yeah,
flux.
so Robert Cameron has work where he makes some assumptions about the magnetic field in the interior and uses a gauge, like a surface.
He doesn't really make assumptions about the interior. That's the beauty of your work. You just apply Stokes' theorem, and you can say something about the net toroidal flux of the hemisphere by only considering the surface integral.
Right, but you have to assume the magnetic field is zero at the equator, and you have to assume that it's also zero at the interior.
I mean,
point. So there are you have to make some assumptions.
I mean, he doesn't assume it's zero at the equator. He has some parameterization for exchange between hemispheres and shows it's not very sensitive to it. The polar part along the axis doesn't contribute, and you assume beneath the tachocline somewhere it disappears, which is not a very strong assumption.
So what I'm trying to say is that that is a pretty binding thing.
Yeah.
You have to make assumptions. It has assumptions about the internal structure, but even with those assumptions, I think it's a pretty strong.
I mean, the main conclusion from that analysis is that the surface integral, what we see at the surface, determines the net toroidal flux. If you have dynamo processes somewhere hidden in the convection zone, they produce a mixed polarity toroidal flux, but they cannot change the net. And his argument is, since we have so few violation of Hale's polarity rules, it's very unlikely they have a lot of mixed polarity toroidal flux, unless you find a way to always hide the wrong polarity somewhere that doesn't pop up with sunspots violating it.
Yeah.
So the claim is because the sun is so well behaved, it indicates that you have a net toroidal field which is responsible for all the activity we see, and then the net is produced by the surface integral, and that's the reason why all these stuff matters so much.
Yes.
So I just
Yeah.
really enjoy this kind of discussion. The way I think to make progress is to really try to refute models. I think it's no good moving forward on the dynamo problem just showing something's compatible with a certain, sort of half-baked, half theoretical, half. And I'm not saying this is what you're doing. I'm not talking about your work here at all. Anthony. But I think in order to make progress, we have to start throwing out models. We have too many. And so the way forward, I think, is to try and think of ways in which new observations, new arguments like the one coming from the thought experiments that you just mentioned, whether we can really get rid of some models. And it's the same thing in coronal heating. And I think actually almost everything in solar physics these days would benefit starting from the idea of trying to refute models instead of perhaps developing new ones at this stage. So it's just a thought, and as I said, it's philosophical, but this stuff is so interesting, I just couldn't help bringing it up. Thank you again.
So I have a quick question. So all these analyses you've been using the sunspot data basically to determine the tilt effectively. Is that right?
Well, no, I mean, a lot of it is just coming from the calcium K. Like, it already shows you the shape of the region.
Right. But
And
the
that
tilt,
basically gives you the tilt.
the polarity is based on the sunspots, right? And so therefore the tilt is effectively from the sunspot tilt.
Well, that's what you kind of originally think, but when you actually do it, like, a lot of them get the correct tilt purely from the shape of the plage, but you don't actually need the polarity. I mean, of course, you might get the plus and minus the wrong way around, but because they mostly follow the same.
Yeah, but I know there's a systematic result that is, if you use magnetograms, the tilt will be larger, systematically higher than the what if you use sunspot data. So how would that affect your conclusion? Would that affect your conclusion?
I'm trying to remember whether
it's tilt is the dominant quenching versus the latitude quenching. Would that affect that conclusion if you were underestimating the tilt?
So I mean, because I never used although I used sunspot data in the sense that I took the sunspot measurements, I didn't use the positions of the sunspots. So I think, I allowed, in this top plot, you have this kind of faint region, and this is basically the error allowed for in the position of the sunspot. So essentially, I think that will sort of cancel out that effect. But it's definitely true. The sunspots are less tilted than magnetic kind of centroid.
But not all Mount Wilson measurements are in the umbra.
I thought they
So I
were,
think
but I don't
what you're using, because I have also looked at those drawings. So remember that in some sense, what they're doing is they use calcium to identify those two-dimensional vessels. And then they use Mount Wilson measurements, single point measurements of magnetic fields in active regions that not always are, actually, there is a significant amount of them that are not explicitly on the darkest part of the umbra to fill those vessels. So if you have more than one measurement per vessel, you start bleeding positive and negative into the. Is that a correct interpretation?
Yeah. So
you start bleeding positive and negatives until the vessel is completely painted.
Yes, exactly.
But the endpoint, the source of polarity, is given by the Mount Wilson single point measurements, and a lot of them are actually. I think that for a lot of active regions, there is more than just the sunspots. There is also. Sometimes there is a little bit here or there that whatever that they were looking at. And so the way you actually color, like in paint, the polarity captures has more information than just the location of the sunspots.
Yeah.
And because the strength, the intensity of the magnetic field is given by calcium, then these tilts are going to be less sensitive perhaps to the specific location of the spot. They're going to be a little bit more sensitive to where people made the measurements those days, but
I mean, they make quite a lot of measurements
Yeah.
typically if it's a strong.
like if you go back to your slide, you can show one of them. It's
Yeah.
like,
Where is it?
it's not rare to see something like this.
Sorry. Here it is.
Yes.
Yeah, so
if you
this
look at
bottom
the
right,
1999.
Yeah. And they can be like that for earlier periods as well. It's just,
Yeah, you have in
There's loads of
1997, like
yes,
these ones.
I don't think I can zoom in
I
here.
think you can see. Okay, in this case, I think there's mainly in the spots. Like there were not a lot of.
Yeah.
Here.
So this is a famous sunspot in 1947, I think. Right?
So these
That's what we had
letters
this-
here, like
yeah.
R2 and this kind of like each one of this is an actual magnetic measurement.
Yeah, yeah.
And in this one, they just made like, well, this is like maybe a more modern and extreme case,
Yeah.
but things kind of like fall between these. And
Yeah, so this 1947 one, they seem to basically make one measurement in each polarity, but there's other regions in that time period where they make multiple.
yes,
So this is not necessarily, it's not like the worst in older times and better.
it's somewhere in between those.
Yeah.
Like in,
To compare the Mount Wilson data, the Kitt Peak magnetograms, and the SO magnetograms, do they overlap?
I haven't tried comparing it with the Soho, well, because I've only looked at this period up till 1985 with the
Yeah.
sun. So the sunspot measurements haven't been digitized beyond that, I think, or much beyond that, if they exist. I'm not sure when they stopped. So we've only been able to compare up to about 1985.
Yeah, I know that an analysis has been made out of SO data about the violators of Hale's law.
Yeah.
That should give for that time period the exact measurement of how percentage of violations really is and how it varies from those cycles that are being observed. I think that would be interesting.
Yeah, I think some people have written about. Have you done something with this, right, with the violations of Hale's law for more recent?
yeah, I did it for
I don't know which.
cycle 20 for 4 cycles, 20, 24, 23, 22, and 21.
Yeah.
And I looked at this. I have a different way of detecting the regions directly on magnetograms.
Mhm.
And it's like human vetted soup, and I did an analysis of all Hale and anti-Hale regions during those cycles, and looking at different. But my focus was slightly different than here. I was really trying to understand if anti-Hale regions are extreme versions of the Hale regions. Like if you have a Hale region and you start tilting it, eventually it flips.
Yeah.
So I wanted to know whether anti-Hale regions in these 4 cycles were just that, the tail of a distribution, or a completely distinct distribution. So that will imply that anti-Hale regions are not just Hale regions that were overly twisted, but they're actually coming already anti-Hale. And so that was what I was looking. And the conclusion is that yes, they have to come from a different origin. They are not. There are 2 distributions, they overlap. So there is obviously some of them that will be just regions that were completely flipped, but they cannot be explained by a single origin.
Good.
So I guess it's getting late. Let's thank the speaker again. Thank you. Recording. Sorry, I started recording late, so